Hi, everyone. Okay. As usual, we'll start at 11:10. So see you in a few minutes. Okay, I think we should start. Today we're going to talk about assembly. So I hope some of you already start to learn about assembly. So that today you're going to learn more. I'm going to formalize some of your knowledge, and the next 3 lectures will be all related to assembly. As usual, my request, at least for some of you, please turn on your cameras if you can. Has really helped me a lot, so I can see whether you guys lost or not, and whether you are like puzzled with what I say. I hope at least some of you can turn on the cameras. Okay, so let's start. So we are on exam. A few bit of logistics related to the course project. As you know, the big component of this class is an assembly programming project you're going to do over several weeks. The exact details of the project will be posted next week. We are finalizing some details there. And the project will be due end of the term. Project logistics, some basics here. Projects will be done individually. Results are reported in 2 stages. Each stages, so you will come to regular labs as you would come to the labs, and you will report some intermediate results, and that will be outlined in the write-up. And each of the stages will report it in 50%, evaluated in terms of 50% of the total grade for the project. And another important thing I want to outline is the fact that the code works alone doesn't guarantee anything. So you would need to come and explain on how you build your code, why certain things designed certain way. If you do it yourself, it's usually not a problem to explain how you did it, but be ready, because without that, your grade might be very low. So submission will be as usual on Quarkus by the start of the lab, and there's no separate pre-lab report, just your code for the assembly project. Any questions about the programming project? So you'll get a chance to get something small but real using assembly. So this is a little bit more advanced than using just circuits alone. Okay, no questions? Can you guys still hear me well? Is documentation a good question? I think that all the details will be in the proposal. Usually we don't require in this course too much details, but it's just a good practice for you as a software engineer to write at least some basic documentation to what you do. So at least the interface and how to run it and what to expect is clear. So I think that should be a nice habit independent from your grade. But how much we're going to evaluate this, you will see in the handout.
I just want to jump in and point out that the last ones are actually just for the labs and not for the project. So for your final project, you will be required to actually talk about your submission. So it's not going to be just your code. We'll detail how you're going to explain your code or walk us through your project for that in the handout.
Yeah, thanks, Mustafa. But really, even here, when I said no separate pre-lab report, just your code, it doesn't mean that you submit your code and you're done. You don't need a report, but you would still need to go and defend on what you did, your implementation. Okay. Okay, let's move on. By the way, it's nice that Mustafa is with us today. So he will be given a lecture next week. So be ready. I'm not going to be the only lecturer for you this term. Okay. So where we are. So we gradually build up everything from transistors, as you guys remember, and go to gates, circuits, and finally we're at the top of the pyramid. And today we start to talk about assembly language. So why is that important? So essentially, the assembly language is the big part of what we're learning in this course, and we already learned a lot of basics. Now we reach the stage where we understand the machine code and we can start programming to something real. So essentially the things to learn and understand for us is control unit signals to the data path, something that we covered in the previous lecture. we talk about machine code instructions, and you've seen essentially machine code instructions already. And today you're going to look at the assembly language instruction, and we will program in the assembly language. Essentially, this is a goal. So how things fit together. So data path signals, that's the one that drives the execution. They come and produced by the control unit. This is something we covered in the previous lecture. And the way we decide that some signal needs to go through the control unit, we need to have an opcode, the instruction that tells us that something needs to be done in terms of control. And this opcode is coming from the machine code. Again, remember the machine code instructions we've seen before. We extract the first 6 bits and they tell us what to do for each opcode. And then the machine code is actually converted directly from something called assembly language. So at the top of this build-up is the assembly language that we're going to spend time today. And this is how machine code instructions look like. If you're on Linux, if you take a binary and you run an objdump on this binary and switch to hexam mode, that's what you're going to see. That's in hex, but you can convert it in binary if you prefer binary. I'm not sure how many of you like to code this way. Maybe you do. But because that's not as convenient to humans, people invent intermediate languages like assembly languages. And it's not a single language. It's actually a family of languages that people use to program machines at a very low level. So again, a basic reminder about the machine code. We covered some of that today, but before, but not everything. So when we work on at least MIPS architecture, machine codes are 32-bit binary instructions which the processor can understand. And hopefully, after what you learn in this course, you will be able to understand too right now and can decrypt if needed. All programs, C, Java, Python, any of your favorite language you have, eventually are anyway translated into the machine code, either by a compiler or interpreter or some other level. But at the end of the day, everything becomes machine code. There's no miracle. So if so essentially, if someone tells you, oh, I'm just using just-in-time Java and I don't really have machine code, that's an illusion. Someone create a layer of abstraction for you that you're writing with some other pseudo-level code, but eventually everything is translated into machine code. I think we have a question here. So the machine code is the op, eras, ts, stuff like that. Yes, that's the low-level machine code. And remember, this is really an interpretation of the machine code. So the machine code itself is essentially zeros and ones, but those zeros and ones we interpret into some way that we can read. And that's what we did in the last class, right? When we interpret the instructions, right? But yes, you're right. This is pretty much what the machine code is. And while executing, the instructions of the program are loaded into the instruction register one by one. Remember, we get through the whole flow of their MIPS-like machine. When we get their, we had a pointer to their current instructions, PC, and then we had instruction register where instruction stored. And there are different bits of that instruction we can decode, right, after we fetch the instruction, and we can read and understand what this instruction represents. Is it I type or R type or J type, and what to do with it. For each instruction loaded, the control unit reads the opcode and sets the signals to control the data path so that the processor works as instructed. And we learn the control of the data path at the very low level again in the previous class. So essentially, the assembly language is just one level on top of the machine code, but it's a very low-level abstraction in the sense that everything pretty much maps one-to-one. That's what we usually say. In reality, sometimes things, one assembly instruction can map into multiple instructions in the machine code, but it's a very straightforward mapping. For example, we essentially assume that each line of assembly corresponds to one line of code. That's what all slides says. I'll show you some examples where not completely true. But basically, assembly is a user-friendly, although it's funny to say for people who program in Python to call assembly a user-friendly interface, but that's the way we position it, is a user-friendly way to write machine code. Believe it or not, when the assembly was invented, the people show it's like a miracle. It helps a lot of people to program better code, because before they were writing in the machine code. So anyway, so for something like C equals A plus B, we're gonna have essentially some registers involved, right? And there are multiple steps here. So you can see, so for assembly, if you had that, you would need to, under the assumption that A is stored in the temporary register T1, and I'll explain you the register soon, the formally everything, B is stored in the temporary register T2, and C is stored in the register T3, then the way we write this instruction in assembly is add T1 and T2 into T3. What is G type? Those are jumps. Remember, we'll talk about jumps. Just wait. So we already mentioned that this is when you want to jump, like had a long jump somewhere in the code, remember? Yeah, that's a type of instruction. You can look at the previous lecture slides for that. Okay. So how the machine, so there's a question here in the chat. We'll be learning how to store the value in a register into memory. That's a very good question. So I have to put this a little bit aside and explain you why, because we are trying to learn kind of the core, and I explain you the DRAM a little bit, but storing a value into the memory hierarchy is a relatively complicated process. So if there's no caches, you could think about it as a value going into DRAM. But remember, when we talk about DRAM, I explain you how complicated the DRAM is. So things are not trivial, and that's a separate course on its own if you want to learn more about the exact memory operation. Right now, the best way you can abstract memory is thinking there are loads and stores that goes into memory, and from their assembly language and everything you do, it's transparent. You don't care about caches and all of it. You'll care about performance, then you'll care about caches, but from their perspective of how to make it to work, that's not required. So you can think about the simplest possible interface. If you look several lectures before, I showed that the simplest possible way to think about memory is having a basic interface, read the value and write the value back, right? Yujan, is this answering your question? Okay. So what's the difference between the assembly and the machine code, you can ask? Well, the machine code look like this, right? And this is how the assembly look like. And you can imagine this is much more convenient for humans to write in this form than in this form. So there is a 1-1 mapping in this case for all assembly code and machine code instructions. So why do you need to learn assembly? Because it seems to be very low level and not the language you normally would program. So the reason to do it, if you believe you're a CS person and you want to understand how things are programmed, this is the only way to understand how the program really works. Because at the end of the day, everything the computer understands is the machine code that is a direct mapping from the assembly. So if you think something's going bad with your code and you don't understand what the crazy Python Java is doing, at the end of the day, binary code has all the answers, right? That's what really goes into it. You don't need it all the time, and usually you don't need it, but when something is really not working, that's the place to look and go for. You also understand your program performance much better, because that's a real runtime. You would understand how the control flows like if, else, for, while are actually implemented in real hardware. You also understand why eliminating if statements make your code faster, because why if conditions actually complicate things. You understand by learning assembly why pointer is such a natural concept for programming. When you learn C or C++, it might feel like pointer is very artificial, but you remember the C was built on top of assembly and was considered a breakthrough when it happens. And just because it simplifies some of the things you can do in assembly without losing most of the performance. Well, branchless programming is very difficult. When you're going to try to program GPUs, you'll try to go branchless as much as you can, and you can see how difficult it is. You'll understand the cost of making function calls. Before, function was just a nice abstraction. You never worried about how it actually execute. Well, in this, over the course of the next 3 lectures, you're going to learn about that. You'll understand why stack can overflow and what does this really mean, and why all these fancy attacks exist that try to overflow your stack or try to go over the boundaries of your memory, like an array, for example. You understand there is no real recursion in the hardware and how it's actually done. So some mathematical abstractions that you learn from theory classes doesn't exist in real hardware. Like there is no real type. So the float types we use are all actually fixed precision, really. They don't represent the real mathematical float value, real mathematical real value, right? You'll understand why memory need to be managed and how it can be managed. You'll understand why people spend so much time creating operating systems to abstract a lot of basic manipulations. And you'll appreciate more the constructs in the high-level programming languages. You understand the beauty and simplification of them and the cost you pay for that. You understand the simplicity always comes at some cost. And an extra bonus, you'll be able to read this book that I think everyone should read if you're in CS field, The Art of Computer Programming by Donald Knuth. And all algorithms in these books are written in assembly for clarity. So if you want to understand this book, you better be knowing assembly language. About the registers names. So the registers in the machines are numbered from 0 to 31. But remembering which number means what is kind of tedious and complicated. So they're specified by 5 bits of the instruction. By the way, when I say all registers are like that, I mean a specific machine, like MIPS machine we're dealing with. Remember, there are different machines like x86, and there is other RISC machines. They might have that done somewhat differently in different conventions, but at the end of the day, there are always registers, they're all numbered, and there's an interface given to you to deal with it. So for example, in our assembly, we're going to deal with something like T1, T2, V0, and so on. If you're dealing with x86, you're going to have EX, EBX, and other registers, right? But the idea is the same. So the relation between two is really there's one-to-one mapping. So there is some conventions that people come up. So essentially in MIPS, it's register to register mapping. Every operation operates on data in registers, right? That you already probably realized. MIPS provides 32 registers, and several have special values conventions. So there is register 0 that keeps value 0 always. Can someone tell me why do I have the whole register dedicated to one value? I hope you guys not asleep yet, so some of you that you're following. So why do I have a whole register dedicated to value 0? Krotik says for reset, not really. Someone says for null pointer. Null pointer is a bit closer, but that's not the really soul. For move. Someone says in the instruction, don't always take immediate values. It does something like dev null. No, dev null is much more high level primitive. So the closest answer is immediate 0 is too large if you ever need to do an operation with 0. So I think also all the questions, all of this has a little bit of truth, but the closest probably was Sam's response. So it turns out that there is so frequently that we need 0 value in many different contexts. So it's just nicer to have a register that has this, and you don't need to deal with immediate values. You don't need to do anything special. So they just reserve one cheap register with the value 0. It's so frequent. In fact, there are, I did one study for several major benchmarks, and it turns out like 30 to 40% of all values stored as zeros in memory and caches. So it's a very frequent value you have to deal with, and if you know it's 0, it's better to have it explicit. Is it even really implemented as a register? Is it optimized out? That's a good question. It probably optimized out. So probably don't store a register, but the interface given to use register, so that also simplify. The register is the most convenient because immediate can only be as the second parameter, right? So it's just more convenient to have 0 as a register in the from logical perspective. But yes, probably it's implemented in a very simple way. Okay. I don't know how the MIPS implemented it. I wouldn't implement it as a separate register, but there might be reasons why it's convenient. Okay. Let's move on. So then there is register 1 called add that reserved for the assembly language. So you can always have one register to deal with. There is register V0 and V1 for return values from function calls. There are registers from 4 to 7 called A0, A1, A2, A3. They are function arguments. Then there are registers 8 to 5, 24 to 25 that called temporaries. Those are the variables you do most of your operations on. There is something called safe temporaries where you can keep the values a bit longer. Those are registers 16 to 23. There are special registers to deal with memory and function support. GPSP, those are stack pointers of different types and some function pointers. And there are registers reserved for the kernel operation. There are also some special registers like PC, high, low that are not directly accessible. And they use in multiplication and division and have some special instruction for accessing them, but you can directly read and write into them usually. Okay, so this is the conventions we have in the MIPS architecture. I guess one question is to you. You notice that we said for function arguments, we had 4 registers to store the function arguments. What are you going to do if you had more arguments in your function? You probably brought functions that had way more arguments than that. What have you to do? What should you do then? So any ideas? How would you solve that problem? Any ideas? So if I had a function with 6 arguments, storing it to hard drive. Well, I told you how the memory is slow. Hard drive is another 2 orders of magnitude slower. So that's not what you want to do. Split it up into smaller functions. Well, that seems like a nightmare for a compiler to split every function that had too many calls. Any other ideas? So some people probably use assembly already. They should have some idea how to do more complicated. I will come to an interesting direction. Use up to some of the temporary registers. You would want to use temporary register for computation, right? Save to memory. So we're coming closer to what really happens. So if you had too many arguments, right? What you can do, you can have some in the function, you can have some convention and put them on the stack, right? And the stack can be, so someone said cache. So remember, stack is an abstraction. It can be stored essentially in different places, but essentially the stack would allow us to manipulate things efficiently and ideally, you would get most of the parameters nearby in the cache, right? So, but yes, your function can have tens and tens of parameters, right? And there's not enough registers to store all of that. So the only place to save it is memory, and the optimization for memory is the cache. Okay. Okay, let's move on. Please follow me. I will periodically ask more questions that would help you to understand things better. Okay. Okay, those registers essentially are nicknames in the assembly that simplifies your life because their name kind of encode their use, right? So 2 questions. When we do syscall in the lab, it will always execute the value in A0. Is it just designed that way? It's designed this way because it's simple and easy to program. And those conventions helps to deal with, generate code and deal with the follow-up of every function call. And someone asked the question, do we need to recite them? So you don't need to memorize things, right? But the good thing is the convention, if you actually see the logic, you would understand what it is. You don't need to remember which register is what. I'm just telling you this on that slide. So, but that's what physically, they're not miraculously stored somewhere. There's just one register file with 32 registers, right? And they all assigned a certain logical use. And they had nicknames that you would use in assembly. That's what you need to remember from this slide. So technically, you can use any register for anything. So as someone suggests, you could have used temporary variables for function arguments, but again, eventually you would get out of temporary variables as well. But this is a convention you better be following if you want to get good performance from your code and get it reliable. So we translate assembly to machine code. When we write machine code instructions or interpreting them, we need to know which registers value to encode and decode. So what essentially happened when we had an assembly language, right? We read what is there. We found which instruction we had, what the opcode should be for it. And then we found for each register was the register number it is, right? Corresponds to. And this is how we get the machine code. As you can see, the process is tedious, but relatively straightforward. There's nothing difficult there. So the machines are good at it. And some more machine code details. R-type instructions have an opcode of 6 zeros with 6-bit function listed at the end. Remember, this is this convention. So this is 6 zeros here. And this is the function code for add. And although we specify don't care bits as X values, in reality, there's no X values, there's zeros and ones. And most assembly language interpreters will assign them to something like 0. In exam, we want you to write X instead of 0 to show that we don't care about those bits. So this is more for logic, that those bits doesn't matter anything, right? So I wanted to make it clear. So you write X just as an abstraction. So you highlight that you understand those bits doesn't matter in this particular instruction, but in reality, it becomes some fixed bit. Okay. So below is the content for an executable file called mystery.exe. So something executable that you might have on Windows machines. And if you're really curious, you can take this code and try to convert it into some real instruction and see what the results would be like and what it really does. And then you can try this one if you want. And if you can't do the previous one, you can now totally program an executable like this. Don't even need a compiler. So if you don't like compilers and you think they're error prone and tedious and hard to learn, you can just program in binary and hexamal like that. And that would do the job. You can actually write code that would execute like that. And essentially, if you're good at it, you can use a keyboard like that, right? And that's it. You don't need anything else, right? So the assembly instructions are supposed to help you with the people that cannot do it this way, like me, for example, I'm not good at programming just with zeros and ones. So we have, like, for example, loops with some instructions in it written in assembly language, as you can see here, and the assembler are going to convert them into 32-bit instructions. So essentially, the assembly language is located at the bottom of the systems part before the hardware starts to run. So assembly language is the lowest level language that you'll ever program in, except of maybe if you would be building a hardware, you would do something more low level, but that's the lowest level programming that you can have. Many compilers translate their high-level program commands as assembly commands, which are then converted into machine code and used by the processor. Note that there are multiple types of assembly language, especially for different architectures. So when I talk about assembly language, it's just one specific for the hardware we agree, which is a MIPS architecture. But in reality, those things can be different, and different assembly language exists for different machines. Right now, if you build a new processor and a new machine, you will have to specify that assembly language for it to essentially implement it, because without that, people won't use it. And then you build a compiler on top of that and other programming languages, but the first step is provide an assembly language for it. Okay, so one question here is, the thing that converts assembly code to executable is not called a compiler. This is something that that people confuse. They think if I take assembly, convert it to the machine code, that's a compiler. That's actually not called compiler, it's called assembler, because there is no fancy compilation needed. Compiler, as you learn later on, does some sophisticated optimizations on the intermediate representation that you hopefully learn in more advanced courses. But the assembler works like assembling the lines. The mapping here is trivial. You just have each 32-bit basic blob map using some tables. So that's a very straightforward process. So it doesn't require a fancy compiler. So a little bit about MIPS architectures that you're using it. So MIPS is short for microprocessor without interlock pipeline stages. And what's important for you to know that it's a form of a RISC and reduced instruction set compute architecture. I think I mentioned one in the class that there are two different types of architectures exist right now. There's the one that called RISC, reduced instruction set computer, and the one called CISC with C at the beginning, which is complex instruction set computers. And the big difference is the RISC philosophy is that you only add instruction that otherwise cannot be represented with other instruction in the set, right? So you don't add any esoteric complicated instructions. The CISC instruction can have anything complicated as a single instruction. For example, you can imagine that x86 has instructions that can do real loop as one instruction. You can do like search for value or do like char comparison or something like that on the whole loop, or you can do like vectoral instructions. Anyway, the whole point is that that was a philosophical battle between the two big camps, one to be a CISC camp and one between RISC camp starting from 70s and 90s. And it leads to two different architecture branches. So there are everything that's Intel and AMD built, that's typically CISC architecture. And this is why their ISA manual for Intel architecture is that large, right? That's how large is the number of instructions they have. And then RISC architecture, all the instructions can, on some of the most simplest ones can fit into a single page. And then trade-offs on what you need to do architecturally for one and another. Like RISC relies on the compiler a lot to do a lot of optimizations to be efficient, while CISC architectures are much easier for compiler because you can just map the whole loop into a single instruction. Okay, so MIPS is a RISC architecture. If you're curious about where the RISC architectures are used, your cell phone is probably a RISC architecture with a high probability. Yeah, so someone just, I guess it's Mustafa said Apple is back with ARM. Yeah, so ARM processors are everywhere right now. There is this whole battle in the cloud right now, whether the RISC architecture can not only be used for the phones, but actually can be used in the cloud. So you've seen on one end, NVIDIA is trying to purchase ARM, right, and Mellanox, that's their bid for cloud. And on the other end, there is Intel and AMD that purchase Altera and Xilinx. So this is the big war that happens in the Silicon Valley right now for who's going to dominate the cloud. And RISC and CISC is a part of that battle as well. So essentially, MIPS architecture, coming back to our lecture, provides a set of simple and fast instructions, and compiler translates instruction into 32-bit instructions for instruction memory. And complex instructions are built out of simple ones by the compiler and assembler. So So complex instructions are built out of simple ones by the compiler and assembler. That's a big extra burden for the MIPS compiler. So we had a question here. Why ARM improves faster than x86? Well, some of these things not just fundamental, but just engineering. So for a long time, x86 was dominant. So essentially, Intel was fully controlling the market, and the market was literally just desktops, right? That was the biggest market. Until we reached the era of small smartphones, and I don't know whether you read the history of one of their, Intel CEOs, former CEOs, who said that his biggest career mistake was when Steve Jobs came to him and offered to build a processor together for Intel chips. His response was, there's no market for that. Nobody's going to buy those devices. So essentially, the rest is history. Like, you know how many people are using smartphones right now. But the bottom line is that for a long time, Intel was the place to go to build processors. and ARM was at the peripheral and was used for really small, cheap devices, because the one advantage of ARM, it was simpler, right? So as you can imagine, if you had a very complicated instruction set, you need to have a hardware that does this decoding for you and can support this complicated instruction set. And that can be acceptable for certain power budget, certain form factor size, like your Intel chip is this size probably. And then if you're low power and you need a really, really simple chip, that what CISC offers is just not going to go. So CISC was for the top performance, and for a long time it's considered to be the only way to go. And then for phones, power was always a limiting factor. So ARM was a good fit for the phones, but people at ARM didn't stay there. They keep improving their system as well. And eventually, if you fundamentally look at the trade-off, RISC architecture shouldn't be fundamentally worse than CISC in any sense, but if the compiler is perfect, and making compiler perfect is a non-trivial endeavor. But compilers build over time and people get to a certain infrastructure. There are also some dependencies on some other components that you never think about. Like say, if there's an interface with memory, for example, if I had an ARM chip, I would need to use other solutions for their what is located on the chip, like SoC, for example, systems on a chip. And before that didn't exist for ARM, it only exists for Intel. So there are a lot of engineering things. But step over step, ARM was getting ground over Intel. That also helped because Intel was making some, I would put it, questionable choices on where to invest and how to, progress. And that allow others to keep up. Like you see, like AMD chips are now competitive, if you ask me, against the recent Intel chips. And for a long time, AMD was always behind. And but right now it's not true anymore. And then ARM is also keeping up in this race, and that battle is going to be interesting in the next few years. Yeah. Any questions here? Okay, so that, just to summarize that, ARM improved faster than x86. There's no like one simple answer. There are multiple dimensions to it, and none of them are in research or development. Some of that is just a pure engineering of availability of certain parts of the stack. Okay, so what is the layout of the assembly code? So something we're going to see when you deal with assembly, there's going to be different segments, right? There's going to be a data segment where you allocate the data. And for example, here, the data segments has an array space, and you can see all the complications with data type you never think about are there. For example, when you allocate a rate of 100, you usually think about this as being something that takes 100 elements, but the elements can be different types. So if you had integers of 4 byte, which as the default size for 32-bit systems that we're looking in here in MIPS, then the space needed is 400 bytes, and this is how the data is reserved for array A and B on the data segment. And then there is the essentially the code segment that can have the main function and the loop function, like a loop piece. That this is a preparation of the values, to start executing. And there is some basic manipulation with the loop, where essentially we assign a value b of I plus 1, and this is how it would be done in assembly. So I guess one question to you. So this is how you write it, but is this like a question for you? How you distinguish between data segment and code segment? Like at the end of the day, there is no rules about it in machine code. So how do you believe, is there any restrictions like here? So how we do know what is what, and is there a way to violate these rules or not? So the short questions, are those rules are written in stone and you need to follow them, or it can be bypassed and you can, misinterpret things? Any opinions? It's an open-ended question. Okay, I'll ask then. So Sam says, is this just a convention maybe? And the answer is yes, this is really a convention. So So the problem is that so essentially everything I described here is just a matter of convention, right? As you would see, there's different segments, like say data and instruction segment, but in reality, you can force the program to behave any way you want. Like for example, when I was, I think an undergrad in my first year, we were given an assignment to essentially to write, and we were also studying assembly, x86 assembly. That was like a long time ago. But essentially the goal, the assignment was to write a virus, the virus that could actually can infect other files. And one trick about, one thing about it is that one way when you learn about basics of how to write viruses, for example, if you want to understand how the infection happens, at some point what happens, you use tricks to misinterpret things. So you essentially try to interpret instructions as data and data as instructions. So you can, for example, inject part of your code into the data segment, and then you just hijack the jump, and they just bring the jump into the place you want, and then you just start to execute from the data segment, right, as it is code, and you can make it a valid assembly instructions there. And essentially the basic virus I wrote was literally just cloning itself. So it was just reading the existing executable, and was just whenever you run the thing, what I was doing, I would first need to detect whether the file is already infected or not. And if it's not infected, I was injecting my own code of my virus, right? That will just had a code how to clone itself, right? This is a basic, fundamental, yeah. And yep, so Mustafa is saying that's how you would do overflow attacks. And yes, that's what you would do. So that was part of the assignment. One thing I want to say, this is all conventions. These are very good conventions to follow if you want to write a good code, but and reliable code. But if you want to actually manipulate someone's code and write something, tricky, remember that people can interpret this any way you like. So you might sometimes see crazy code when it jumps into the data segment and try to execute there. That is something that viruses do all the time. Okay. Anyway, so this is just examples of the syntax you would use. And this is like a basic loop manipulation. So what are those sectioning that exists here? There's a data segment that indicates the start of the data declarations. There's a text segment that indicates the start of the program instructions. There's the main, that initial line to run when executing the program. And you create other labels as you need, and you can have a full control over where you jump and how you execute, right? Remember, for the machines, everything is just an instruction. So if you give it a PC to the instruction that is in the data segment, it's going to read it as normal, unless you had some hardware protection against that exists in some systems. But generally, if nothing is protected, you can jump anywhere. Okay, some things to know about MIPS instructions: that instructions are written as an instruction opcode and parameters. Each instruction is written in its own line. All instructions are 32-bit, 4 bytes long. I hope you remember that by then. I said it so many times in different lectures. Instruction addresses are measured in bytes. So starting from the instruction at address 0, so everything starts from 0 and then go positive from that in some form of an offset. The following tables show the most common MIPS instructions, the syntax for their parameters, and what operation they perform. So what are the most, so here I just add a table from a famous Patterson and Hennessy book that shows you the common arithmetic instructions and how frequent they are. Remember, this is collected from some representative set of benchmarks, and obviously it depends on the compiler you use, the code you wrote, but they average across many applications, so the numbers are quite stable. So as you can see, there is a lot of arithmetic instructions, right? Something like add, sub, and die. And they use as operations in assignment statements, right? When you store something into the value that's arithmetic. And so their integer frequency is like 16%, and their floating frequency is 48%, okay? Then there are data transfers. So different loads and stores, right? Byte, word, and others. This is reference to data structures such as arrays. Very frequent, as you can imagine. Most of the compute manipulates with some data structures and memory. So 35% are integer and 36 floating point. Integer versus floating point is somewhat biased because that's probably done on spec benchmarks, right? And those has a lot of floating point, which you probably don't run as much, but some other people in scientific computation will do. Another thing is logical, so and, or, nor, and others is in assignments. They are frequent, but not as frequent as integers, and you see there as arithmetic, and you see that most of them are integer and very few are floating point. And then an important thing to know is conditional branches. So if you think about how frequent are the branches and how important it is to handle them, why branch predictors exist in hardware is because they're so common. They use if statements and loops, and it's hard to imagine any sophisticated code without loops and if statements. And because of that, there are 34% of them overall. So most loops, I see the dominant number of them as integer, but obviously some floating point. When we say that every single instruction is a branch, remember, you might not have a direct branch written, but you write a loop or an if statement, and that's going to generate a conditional branch, right? And you can see this is a significant portion of all instructions. And then there is these long jumps that need for procedure calls, returns, case switches, and all the other complicated things. And as you can see, this is way more rare than everything else. Okay, any questions about this table? So this is to give you a feeling on which instructions exist and how important they are relatively to each other. Like everything needs to be supported, but some things are more important than others. Any questions here? Okay, so arithmetic instructions. So we have all these instructions like add unsigned, add-I, and so on. And that's either opcode and functions. Again, you know that some of them that doesn't have opcode of 0, then this constant here, like for add, this is really a function. And this is their syntax. So for example, if you had, you know, add or add u, this is the syntax, right, that it represents. And when you have something with add I with immediate value, the immediate value here, the value I, is sign extended. That's what SI stands for, sign extension. And there's a division, multiplication, subtraction, and all of them has a certain, you know, meaning. That's what's written in the, say, instruction set manual for each architecture. And this is, we operate with very basic instructions, so things are relatively straightforward. This is the division that is a little bit more complicated, right? Because there is 2 results here, right? The remainder and divisor. So that's stored in the register low and high because there are 2 results. Same problem with multiplication because the results might not fit into existing register. You need to have the output that consists of 2 specific registers, and then you can manipulate with them and decide what to do when the value doesn't say fit into the standard type. There's obviously a subtraction there as well. So high and low refer to this high and low bits to the register slide. Yeah, that I showed before. Okay, so LU instructions. Note that for LU instructions, most are type instructions, and the 6-digit codes in them are zeros. So that means the opcodes are 6 zeros, but the function codes are the bits that store their type. And exceptions are the I-type instructions like add-I, and-I, and so on, because those you would have one immediate value as the parameter and you use the real opcodes, they are non-zero ones. Not all R-type instructions have an I-type equivalent. So RISC architecture, so don't expect everything to be replicated. RISC architecture dictates that an operation doesn't need an instruction if it can be performed through multiple existing instructions. For example, division by 42 by the immediate can be done in this way, right? So this is why this instruction is not exist. So you don't have, you know, divide instructions. Yep. Okay. Any questions here? So some instructions are not done because that's not needed. Okay, then there is logical instructions, right? Logical instructions are usually similar in spirit, but they just had different manipulation patterns. So they use zero extensions, pad everything with zeros for constant rather than doing sign extension. That's the difference with arithmetic instructions. And that's especially important when we're going to talk about shifts. So a good question from Yujan, does this mean that RISC doesn't really need sub-I, mile, others, since you can do all of them by ADI first? You're right. So in reality, it might mean that it's just SAML that exists for conventions, but in reality, there is no RISC instruction for that. So the assembly might have them, but in reality, they don't have a physical instruction for them. Oh, you're saying, can I do them by addition first? I would say that the trade-off is not religious. So if every instruction would cause two other instructions and that would be significantly more costly, that's a bad idea to do. Like an example here is that divisions are very costly instructions, can take tens of cycles. So doing another addition with a constant is very cheap, right? So it wouldn't delay that significantly. But replacing any sub with some additions and constants would be, you would be hurting performance by 2 to 3x, right? Depending on how many instructions we'll use. Does it answer your question, Yujan? Okay, so I think we reached the 12 p.m. mark. So let's have a 9-minute break and I'll see you back at 12:10 and we'll continue into logical instructions. think there was a question that Mustafa already answered about zero extension. Just a general explanation is the reason why when we did with logical instruction was use zero extension is because, as Mustafa said here, logical instruction doesn't really want a special interpretation for the sign bit. When you're dealing with and or, bit 30, bit 31 doesn't have any meaning to be different, right? I manipulate with values being as unsigned values. But when I'm dealing with arithmetic instructions, some of them want to interpret their registers as signed values. And because of that, we need to do a sign extension to preserve the value, right? Or interpret the value the way we want. Okay, Jeff, does it answer your question? Yeah. Okay, let's move on. 10. So logical instructions. So as you can see here, we support all the usual and I, nor, or I, and others, right? This is the examples on how they're done. And the interesting things are shifts. So shifts can be of two types. There can be shift right logical and shift right arithmetic. And their parameter, so they denote it as SRL and SRA. And the V denotes a variable number of bits specified by the register S. So why do I have two different shifts? Why do I have both logical and arithmetic shift? Is because when you shift to the right, there is a need to understand one with how do they fill the gaps. I shift and I have some bits that are now has no meaning. I need to shift something. And I can either shift 0 or can shift a sign bit. That's where they're fundamentally different from. So this is the explanation, and that's very frequently people get confused. So please spend some time on the slides to get it right. So the left shift, same that essentially it fills empty spots, lower bits with zeros. This is why we have SLL, but we don't have SLA, right? There is no meaning to fill in the empty slots on the right as we shift to the left with anything other than zeros, right? Because the meaning of when we shift by say by 1, we want to multiply by 2, and we want the extra bits from the right to be zeros. So this is the normal logical operation. But there is a difference when we shift to the right. So when we shift to the right, there is a logical shift. So what happens is if I had the value like that, right? And for simplicity, this is just 8-bit. So this is a least significant bit. This is most significant bit. So each of these bits moves one position, but then there is this bit that doesn't have a value, and we need to get it somewhere. So the logical shift fills in those values with zeros, because that pretty much would represent as I would logically move, and I want the value to become smaller, and the value doesn't have a sign. So there is nothing I need to do for that other than filling it with zeros. But arithmetic shift is different. The arithmetic shift fills empty spot, higher bits, with their MSB of the original number. So the MSB is the most significant number, and on their integers that are signed, that represent the signed bit, right? And the arithmetic shift, when you do it, you want to keep preserving that bit. So if it happens to be, so when we shift arithmetically, that most significant bit shifts here, but also it's copied over here. The main reasons why we want to do it this way is because I want to preserve the sign. If the value was negative, I don't want my arithmetic shift by shifting it and making it, apps of it smaller. I don't want to change the sign, right? So if it's negative, I want to stay negative. So this is why this sign is being preserved in most operations. And this is how you want to distinguish those things. I guess there are non-tricky questions for you that I like to ask students. And I think when I was at TA, I asked students, I think at CMU a lot, and it's very few can answer those questions, but some can. So when you're gonna use your C programming language and you're gonna write a shift, which shift it's gonna be? Is it gonna be arithmetic or logic? So is the question clear? So if you write your C code, right, and you write a shift there, which shift it's going to be? Well, I had 4 people going for logic. One person says, the hand says, depend on the type. But when you write in C, there is nothing that you could write in the type. You literally just write, the syntax doesn't have a way to express arithmetic versus logic, right? There's just one shift. Any other opinions? Okay, so why is this a tricky question? So there is, someone says, depending on whether the number is signed or not. That's probably the closest that you can answer. But the honest answer is that it's compiler specific. So the compiler, there are several compilers that that's essentially specified by the compiler rules, right? So you essentially, the compiler can interpret one way or another, or had a more complicated interpretation of the data type. The problem with the sign and how to interpret, imagine people will use constants, right? And they shift them by certain values and things like that. Any constant can also be interpreted by signed or unsigned, so it complicates things, right? So sometimes compiler will have to resolve that complexity. So in some compilers, they just, if they cannot resolve the data type, signed versus unsigned, they just go to some default mode, which is typically logic, but it's not guaranteed. So anyway, what I said, this is another reason why you need to understand compilers well, because you can get some unpleasant surprises there. Okay. Okay, let's move on. So the data movement instructions. So we had instructions like mf high and mf low with some basic syntax with just one parameter, and then they can read the registers high and low. Remember, that's the one that we get when we had special instructions like division or multiplication. We can also move in the other directions. These instructions are operated specifically on the high and low registers described before. So we cannot use them as parameters directly, but we can read and write into them with the special for instructions. And now there's time for even more instructions, branches, loops. So control flow in assembly. So not all programs follow a linear set of instructions that all of you know by now. And some operations require the code to branch to one section of code to another using if-else instructions. And some require the code to jump back and repeat the section of code again. This is typical for and while loops. And for this, we have labels on the left-hand side that indicate the points that the program flow might need to jump to. And reference to these points in the assembly code are resolved at compile time to offset values for the program counter. And those are the examples of labels you see, like main and loop. Right? Okay, so those are the branch instructions, right? Several examples of those. Branch when equal, branch then, greater than 0, branch that less or equal than 0, branch that not equal, and so on. Branch operations are essentially key when implementing if statements and while and for loops. The labels here are memory locations assigned to each label at compile time, right? And the note is that I is calculated using this formula. So let me explain what's going on here. So essentially, when we want to move things, we had essentially parameters that we use for comparison. So S and T are compared for equality. And then depending on the results, if it's true, then we want to change the program counter to a certain position that's specified by the label. And then essentially the variable I is calculated using this formula. So it takes the label, right? And it does minus current PC plus 4, and then shift it to, right? So to, I guess I'll ask you, why do we shift it right to positions? Yeah, so Yujan is saying, why do you shift this and then you shift back? Perfect questions. I want you to answer it, like not just you, Yujan, but others. So why do I shift to the right here and then I shift to the left here? So what do I get with that? So someone did it, we got the last 2 bits cleared. Right, that's correct. We get the last 2 bits cleared to zeros. Why are we doing that? What is the meaning of this? So you get it right, that's they are nullified, but why? Yes, PC needs to be multiple of 4. I don't want to jump in the middle of the instruction, right? So I want to make sure that with this manipulation, and labels can be anything, they always round it. So I don't want to be on the position where in the middle of instruction, I don't know how to interpret it, okay? Okay, so this is how to interpret this, and they're pretty much all the same in terms of where you branch, right? The only difference is the predicate that's used to compute this, right? Sometimes have 2 parameters for 2 values, some just had 1 parameter, they compare with 0. And there are also comparison instructions that generate the predicate that can be used then for jumps. So comparison operation stores a 1 in the destination register, and the less than comparison is true, and stores a 0 in that location otherwise, right? So this is just examples of that. So you do comparison and you store 1 if the destination in the destination register if the less than comparison is true, okay, and store 0 in that location otherwise. So that's how you interpret this. Okay, so this is what that goes into the destination register, right? There's one aspect of it. Remember, I said everything was mapped 1-to-1, and there was a valid questions about why certain instructions are not implemented using others, because that would make us follow more religiously the risk philosophy of having only non-redundant instructions, essentially. So what we list in the slides are pretty much real instructions, and each one has an opcode corresponding to it. But there are some pseudo instructions you're going to see for convenience, which don't have their own opcodes, which are implemented using real instructions, and they are providing for just coding convenience and ease of programming. For example, if you had branch greater than and equal, something like that, you're not going to really have that. What you're going to do, you're going to use a proper comparison instruction that would compare these 2 instructions for less than, and then you will take the output of that instructions, T2, and use it for branch equal, right? So essentially, you would really just do comparison between the registers here instead of having this instruction, and then we have this instruction here. Okay. And obviously, we need to have jump instructions that jumps using the labels, and there's the different interpretations of labels. There's jump, regular jump that just take a label and jumps to this label. There is jump and link instruction that uses array registers, stores the address that's used when returning from a subroutine, and this is how we remember one of the registers we mentioned as a special registers. And also note that GR and GLR are not G-type instructions. Okay, one complications with dealing with eval statements in MIPS is that the way they interpret conditions are a little bit non-intuitive. The strategy is, so essentially if you had a code like that, if I equals j, then I plus plus, else j minus minus, and then you have j plus equal to I. The strategy for if statements is like that. You test the condition and you jump to if logic block whenever condition is true. So essentially, if this is true, then you go here. Otherwise, you perform the else block and jump to the first line after the if block, right? So this is, so the flow chart would be helpful here if you want to understand it. So essentially what it does, if you do I equals j, there's an if block and an else block and the end. So if that's true, you go into the if block. And if it falls, you go to the else block. And after the if block, you just jump over here. And after else blocks, you fall into there. So that's the best way to interpret the if statement. The only problem is that the branch instruction jump on true instead of false. So negate the check conditions to I not equal to j, right? So that's the special part of the interpretation. So essentially, this is the difference, right? So you need to negate and then you flip false and true. That's how you interpret the MIPS conditions. So for example, this thing, this piece of code would be mapped to this thing. So you had T1 equals I and T2 equals J as the temporary register storing values I and J. Then you would need branch not equal instead of branch equal. So this thing is not converted to branch equal, converted to branch not equal for T1, T2. And that's your L, essentially the else statement, right? And then you do this, and then you do that, right? That's essentially the syntax. So this is how we translate those if-else statements. So we had T1 equal to Y, have this. So this is really line by line how it maps to the assembly code. So branch if not I equals to J. So this is this condition. This is the if part, right? I plus plus. This is the and section to make jump over the else. And this is j minus minus, and this is j plus equal to I. So we had labels here. This is the branch that jumps over if. This is the really the abstraction wise, this is an if block, right? This is the jump to else to bypass that. And this is a jump after you're done with the if unconditional to the end to bypass the else. Okay, any questions here? Yeah, we're going to look at Sam is asking, would else if just have another one of these blocks in the else block? Yes, we'll get to that. We're going to, I think on the next slides, we're going to have more complicated example with multiple ifs you would see it. But yes, you're right. The idea is no like other ways to treat it. You would just have going to get another label. Okay. If we want to change branch not equal to branch equal, then we also need to swap the if and else blocks. That's not always convenient, right? So anyway, so you can write a code like that, and this is your if, then you branch to if label. So as Sam was one step ahead, so what if I had multiple conditions, right? Where that happens, well, for example, if I had a complicated predicate like this, and this is if body, and this is else body, and this is what follows the if statement. So the way we do it, we do I equals j as one conditions, and then we do I equals k as another conditions. And this is if blocks, and this is else block, and this is and, right? And for example, this is, we go here if true, this is false, and if the second one is true, we go into here, right? Because it's or, and that's another direction if it falls, and the second one is false, right? And then we go here. And then we need to do branch and false, so everything flips. We see here. So and this is how we generate the code. And I guess I didn't fully answer Sam's question about multiple ifs, but those are just done kind of from the inner to the outer loop, and they would need to generate different labels. This is more of a complications on when your predicate is more complicated. So we get branch equal of T1, T2 for if, and then branch not equal for T1 and T3, and then we get if, and then we get, and else. And all of that maps to the original instructions, more or less, easily. So this is the way we generate code for if conditions. So you want to make sure you don't get it confused. If you actually follow the logic, you would see that things are, executed properly, but this is where it's a little bit confusing compared to the regular C code. Okay, any questions here before we go into the loops? Good questions. How similar would switch statement be? It depends on how they implement it, because really if each switch statement can be implemented as a set of ifs, right? So it's just provided for convenience. So there is, I don't think that MIPS has a special switch statement. I need some special jumps, but like all switches are usually represented as a long sequence of if statements. Sam, does that answer your question? From the compiler perspective, switch is just a convenience for the user, for the programmer to write complicated if, so not to have a long spaghetti code, right? But it's really fundamentally no different from an if statement. If you go to theory, you would see there's really nothing else needed other than have if conditions and branches, right? You don't need any other logical instructions. Okay. Let's look at loops, and there are different types of loops. There is while loops, there are 2 while loops, there are 4 loops that we typically have available in our favorite programming languages. This is an example of a simple loop in assembly, like a while loop in MIPS. So the way that loop is done is there is a part that's like a pre-header of the loop, that's how it's called in compiler area, where essentially we set up variables to the right starting position. So a variable I becomes 0, right? And this is how we do it. It looks funny, but you don't need a special move instructions to move zeros. You can just do that. And then you essentially do add I with 100 to prepare register for comparison for n. And then if branch equal, we had a branch equal of T0, T1. So essentially when T0 eventually would reach T1, which is 100, we would need to jump to end, but otherwise we would keep adding I++ and going back to the start. So essentially what happens, this is executed once, you set up all the variables for the starting and final positions for n, and then you keep iterating inside of this loop, with this branch, until we reach, T0 reach 100, and then then this branch equal will bring us to this label. This is how this is done, which is the same as in C. If you would write something like while I not equals to 100, I++. As you can see here, when C language was introduced, it was tried to be very close to assembly, actually. So a lot of things now you have in C might have more meaning for you as you understand how the assembly is written. And this is why C is one of the still the most efficient language, because it provides a lot of good features while being as close as to hardware as possible and provides you very good efficiency. So if you want to be in, say, in system programming world and want to write very high performance code, you would need to operate using languages like C or C++, right? Because they're very close to hardware. Okay, any questions here about the loops? Why is there a J beside the start? Okay, anyone wants to answer these questions? What does that J before the start means? Yes, so remember ND, so J is not just one letter, it's actually opcode for an instructions. It's a jump instruction, right? And it jumps to the labels, right? So essentially, but how does it know what to jump or not? It has a flag that it takes to jump, and that flag is set by the branch register. Yeah. So this is essentially, this is unconditional jump, So that always jumps. So the only way, so the condition for branch is set here. And if it's not true, then you jump to end. That's the only way to exit. But this is just unconditionally jump to start. Okay. So it always jumps like it's, yeah. So the question is not quite relevant, but said, I heard that ++I is faster than I++. Is it explainable in assembly? I think what you're talking about is not related to, say, C language, but probably C++ or like Java languages, where ++ is not a simple addition, right? But it actually does manipulation on a more complicated structures like iterators. So there might be way more logic that goes into ++. So where you first take, a abstract pointer or an iterator to the object, and then you do something before later. If it's just an integer constant, integer variable, that ++I versus I++ doesn't make a dramatic difference. Right, it might be an extra copy, but like otherwise it's not that different. Okay. Okay, now we're considering a for loop. So for loop, we had initial conditions, the setup of the variable, then conditions that won't compare, and then the update, and then the for body. And the for loops, such as above, are usually implemented with the following structures. So we had a main, and that's the part of the init, right? And then there are if not condition here, right? Then we branch to an end. So if condition is not true, otherwise we do the for body, and then there is do an update and jump to start, right? Why compilers don't like the for loops is that they might, in the for loops, is that there is a lot you need to do at the beginning, because it might be the case you never execute the body of the loop, but we're executing this part. So you always need to execute this, even if you don't execute the body. So essentially, there's a lot of, there is some repetition there, as you can see. So we set J to 0, set A to 1, and then we set T9 to 100. And then we had this branch here, right, that checks I equals 100 conditions. And then we had J equals J plus 1. How do we get that? So T1 is here, T1 is J, right, logically. So that's where we increment it, right? T1 by T0, and T0 is, where's that? Yes, so that's the one. So it says J equals J plus I. So T0 is I, and T1 is J. So this is J equals J plus 1. And plus plus happens here in the update state. Okay. And essentially there is a, this is the branch that exits the loop, right? And this is the increment update of their update phase of the for loop, right? So this is what logically happens here. Any questions about the for loop? I said it's an exercise, but I guess I did it all for you. Okay, so this is how you do loops. And I guess, yeah, the question here was that I was, I guess, planning to ask you is, what's the real conditions here? And I think that's relatively straightforward. There is I equals 0, right? That's what we say T0 to 0 at the beginning, right? And then I not equals to 100, that's the conditions of the stop, right? And then you have I++, that's what you happen in the update stage. And here you clearly had J equals J plus I, that's been in the description here. So this is what the C code translates into this assembly code. And as you can see, this is not that much worse visually than this. It's still readable. Unfortunately, when you start to iterate with more complicated data structure, this becomes more and harder to read. Yeah. So while loops are pretty much the same without the initialization and update sections, so they are simpler in that sense, and so on. So how does it know when to call the update? That's a good question, and the answer to that, it doesn't need to know, because the update is anyway called if you don't exit, right? So essentially, it just, for our own conventions to explain what is what, we had an update, but there is really no any branch to update alone, right? So we just execute this, and then it goes to the next line. This is just a labels for convenience. You're gonna see that that extra label might be not needed here, but it's for readability purposes, it's actually quite convenient. So you understand what is the body of the loop and what is from here, right? So those labels are good for readability of the code, and they're automatically generated. In some cases, in some instructions, there might be jumps, just goes into the update by bypassing something, but not in this case. In this case, Terry, yeah, this is just for convenience. So you would know which part is which, right? So it simplifies you reading the code. So, so another exercise for you, and this time I will let you give it a try. So try to take this code here in and convert this into the assembly. So this is a Fibonacci function. So essentially for n equals 0, that's the initial two conditions, and this is a while loop you need to write. Right, so what I ask you to write is the corresponding assembly code. So it's a few lines of code, but still I would give you a few minutes to try so that you can do it yourself and see how it goes and how different it's from what we have. So whoever is ready, send your response into the chat. Anyone has any questions? Please ask in the chat as well. Okay, anyone has anything? Yes, you can use V0, V1, yeah. So you can use V0 here if you want. Okay, I'll wait for a few more seconds and then I'll show you the answer. Okay, anyone has any answer or at least partial work done that you want to put in the chat? Okay, so that would the assembly would be, right? So you can't, so what you do here is here's the C code, right? And this is the assembly code. So this is how you initialize something to 10, right? And then you, so this is done as a separate model. So we don't need to return it correctly. You just jump to the end of the loop and then that's it. Just store the results here. So, so we don't really follow any complicated conventions here yet, but you see, this is how we set up the constants, 10, 1, and -1. And then this is the loop, right? That needs to be branch equal because there was non-equal here. So we convert it. The opposite, down loop, if n not equal 0, then we do f1 equals f plus 2 and f1 minus f1, 2. Then this is n equals n minus 1. And then this is iteration of the loop until the condition is true. And then that's the storing of the results. Okay. Okay. Then any questions here? So yes, Yuran said that the harder thing is to manipulate the program stack, but we keep this complexity aside for now. That would happen eventually, right? So this is just arithmetic part of it and loops. Any questions here about how we convert the loop and all the conditions? Okay, so essentially now we can essentially make an assembly program. So we can have a structure similar to Python or C. We can set aside register to store data. They have some sections for instruction that manipulate this data. And it's always good to decide at the beginning which register will be used for what purpose. And we'll cover more on this later. Okay. And that's pretty much everything I want to have today before we go into more complicated material. Any questions about that? Any questions about the lecture today? So if there are no major questions, then that's it for today. You get roughly 10 minutes back and you can work on, on your other courses and assignments. Thanks everyone and have a nice day. Thank you.